One of the most famous examples of technology catastrophe was in the 1985 Michoacan, Mexico earthquake. The ground in Mexico City was moving for a minute and a half, about like this. And eventually these tall buildings had such large motions that they were crashing into each other. And that's an extraordinarily bad thing to happen to a building, to have two buildings collide at some height.
Older buildings are a special problem. Many were erected when codes were minimal or even non-existent. Upgrading their structural integrity while maintaining original appearance and character is tricky. Such was the case with Los Angeles' City Hall. It was the tallest building downtown, 32 stories, when it went up in 1928, 5 years before local earthquake construction standards were enacted. Its top floors sustained serious damage in the 1994 Northridge earthquake. It was a magnitude 6.7. Engineers knew they had to prepare the rigid steel structure for an even bigger quake, which is likely. City Hall sits above an active fault, which was only recently discovered.
It is an amazing technology.
Technology that is deep beneath the structure, accessed by a trapdoor in the parking garage.
What was chosen was a new type of system where the building was basically placed on large rubber discs.
Yeah, you can literally say we picked it up. It's hard to believe we can pick up such a chunk of a building.
Yet that's what was done. City Hall now sits on these highly compressed rubber and steel discs. 419 big ones and 90 small ones called sliders. Enormous shock absorbers are also at work here. It's called base isolation.
Here is what we mean by base isolation, where the building is totally air-gapped from its base environment, and it's only connected to that environment through the rubber bearings.
Base isolation has been in development for more than 30 years. This demonstration very simply illustrates how it works. It separates an object from its base, isolating it from a tremor and its effects. This dry moat that surrounds City Hall is another element of the technology that further isolates the building from the ground. The $300 million project began in 1998. It took 3 years to complete. Dozens of buildings in Los Angeles and San Francisco now rest on isolated bases, waiting for the ultimate test of effectiveness, an earthquake.
Absolutely. To test its limits, the limit of that technology, you need a very good ground motion.
He's certain it can withstand a significant quake, a magnitude 8.1.
I have to believe in my engineering and in the state of technology and science.
Structural engineers are still learning, repeatedly humbled by the Earth and its power. The Kobe, Japan earthquake in 1995, a magnitude 6.9, is an example.
Kobe was a great shock to Japan on many levels. This relatively small earthquake that occurred inland did such tremendous damage that it really caused them to reassess what they were doing. It also showed them that their buildings needed more work than they had thought before, particularly old buildings.
The Japanese are working on promising technology. They are devising buildings whose structural properties actually change depending on the nature of the shaking.
For instance, you can put some diagonal braces in the frames of a building and put some hydraulic valves in those diagonal braces that would change the stiffness of the braces. You can decide when is the best time to tighten or loosen the valve to change the force in that building to minimize the deformation in the structure.
They are called active damping systems and are controlled by computers that detect ground motion and automatically compensate for the shaking. They can reduce the sway of a structure to 1/3 or 1/2 that of a building without such dampers. The high-rise on the left is an example of how this technology limits potentially deadly conditions. The one on the right is an example of a disaster waiting to happen.
There is no building in the US that has a fully active control systems. There is concerns about the reliance on power and standby power and the magnitude of buildings that could be actively controlled. But it's definitely the science that's around us now and its applications of the futures.
The fundamental difference between the Japanese and American approaches to engineering is this. The US accepts building damage, repairing structures when necessary. Japan, which experiences many more quakes, cannot afford to repeatedly fix buildings, so they're engineered from the start to resist shaking. Homes, in some ways, are less vulnerable to earthquakes. Older wood frames flex with motion. Single-story models don't topple over. Then there are those specifically designed with disaster in mind. This house in Berkeley, California was engineered to withstand the forces of a quake. It's modeled on a tiny organism that can adapt to and survive in many hostile environments. It's hoped the home can mimic the qualities of its microscopic counterpart. The structure is a perfect ellipse, allowing loads to be distributed throughout. Among its many unusual features are the walls, which are angled 4 degrees inward to create a low center of gravity. The home was built after the Loma Prieta quake of 1989 and has not experienced a major shaking event. Time and a serious tremor will tell if it's an engineering triumph. Earthquakes have forever given the edge to Mother Nature, not man. But space-age technology is helping to even the odds. Throughout history, technology has struggled to keep pace with scientific theories and ideas, until now.
I think we're poised to do some really interesting things over the next decade, because we're just now able to essentially see in real time whole parts of subcontinents all moving.
Global Positioning System, or GPS, is a high-tech tool that takes scientists way above the Earth to learn what's going on inside it.
The GPS antenna here is picking up signals, radio signals, from all of the GPS satellites that are in view right now. It's about 10 GPS satellites that are being recorded on this antenna.
GPS was developed in the 1970s as a navigation device for the military. Scientists found a different application for GPS, using it to follow movements of the Earth's faults.
For the first time, we're seeing a real-time picture of how the Earth's plates are moving with respect to one another, and we're looking at the complexity of what goes on, especially at the boundaries of plates where the earthquakes occur.
This antenna near Gorman, California, is on one side of the San Andreas Fault. A second antenna, at a different location 1.5 miles away, is on the other. 12,000 miles above the Earth, satellites send readings of the two locations to those antennas. That data is fed to this receiver just a few feet away. The receiver then transmits the information through phone lines to a central computer system, where it and other earthquake-related records are accessed by researchers.
When we get the data back to our offices, we have written computer programs that automate all of the procedures to take the data from all of the stations.
Scientists compare the data from the different GPS sites, looking for inconsistencies that suggest even the slightest shifts in the Earth's crust.
It's changed the way that we do precise measurement of plate movements so that it can all be networked and automated in a way that we could never do.
There are hundreds of GPS sites around the world. One has revealed unusual and ominous movements where plates beneath Oregon and Washington meet.
The GPS sites there are moving in a very irregular way, and the site will suddenly move, and then there will be a few months where it doesn't move very much, and then it'll accelerate and move, and then there will be a few months that it doesn't do that. Now, without continuous GPS coverage, we would never have been able to see that motion.
These results lead some scientists to conclude that the odds favor a catastrophic earthquake in the region, threatening major population centers, including Seattle, which has already experienced frightening ground movement.
Pacific Northwest shouldn't be underestimated because it's possible that a quake there could be a very big one.
While the technology might be new, measuring the Earth's surface movements isn't. For decades, scientists like these at Wrightwood, California in 1993 have dug trenches in quake-prone areas, physically taking stock of what has happened over time. The Earth leaves a tangible record of changes that can be plotted by hand. This method is still used today in conjunction with space-based research.